Melting and freezing and sublimation. So if we look at a solid and we increase the temperature of a solid, the thermal energy of the particles increases. And the thermal energy is a kinetic energy. They're moving, they're just not moving through space, they're just wiggling. So they wiggle more and more and more. At the melting point, the molecules or atoms in that solid have enough energy to partially overcome those intermolecular forces, so they're not stuck in position anymore. They're still close, but now they're able to squeeze and slide past each other. That's melting. So the molecules in ice melting are going to break free from their solid structure and become a liquid. We're going to see the same phenomenon with melting as we did with evaporation, that once the solid starts to melt, the temperature is going to remain constant until all of the solid has melted. So when ice and water are both present, the temperature will be 0 degrees Celsius. So we can look at a heating curve during melting. So same idea here with the temperature and the heat, but now we're starting at a lower temperature. At minus 20 degrees Celsius, water is a solid. So we take that frozen ice, it's a solid. As we heat it up, the temperature increases. We add energy to it. The temperature increases until we get to 0. At 0 degrees, it begins to melt. It's the higher energy particles that melt, and the lower energy particles stay in the solid. So as we add more and more heat, we can speed up how much it's melting, but you can't raise the temperature of the ice water above 0 degrees Celsius until it's all melted. Once it has all melted, then you're increasing the temperature of the liquid. And if you keep going, you'll get to a boiling point, and the water will boil. So we add ice to drinks to cool the drink, right? You don't put ice in something to make it warm, you put it in there to make it cold. Melting is an endothermic process. Melting ice absorbs heat from the liquid, causing the liquid to be cooler. And if you think about melting an ice cube, how do you melt an ice cube? Well, you could stick it in your hand and hold it, right? And put heat from your hand into the ice cube to make it melt faster. Melting's endothermic. That makes sense. The opposite, freezing, is exothermic. That doesn't make sense. You mean when you freeze something, it releases energy? Releases heat? Yeah, it does. It has to release heat. Because otherwise it's not going to get colder. Exactly. And when you put heat into something, it melts. To get it to freeze again, you have to take heat out of it. That's what your freezer is doing. The condenser, the fans, all those things in there are sucking heat out of the inside of the box. And that's why things freeze when you stick them in there. It releases heat, and your freezer has to remove that. Of course, we have quantities for this as well. So heat of fusion. Delta H FUS, heat of fusion. So fusion, it's like we've been talking about melting and freezing. What the heck is fusion? Fusion is a fancy word for melting. I'm sorry, that's what we use. So how do you remember that fusion is melting? Well, think about chocolate chips. If you heat chocolate chips, right, they get soft and they begin to fuse together into one big lump. That's melting. So fusion is melting. Heat of fusion for water is 6.02 kilojoules per mole. That's a lot less than the heat of vaporization, because you don't have to completely overcome all of the intermolecular forces. You just have to overcome enough of them that they can slide around. So 1 mole requires 6.02 kilojoules. This is positive because ice melting is endothermic. The opposite, freezing, going from liquid to a solid, releases 6.02 kilojoules of energy.
Do we have to memorize the heat of fusion
No, you don't need to know these numbers. So we can use the heat of fusion to calculate how much energy is needed to melt a given substance. It's a conversion factor between moles of solid and the amount of heat needed to melt those moles. So calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So we've got a 15.5 gram piece of ice. It's water. And on the previous slide, we learned that the heat of fusion for water is 6.02 kilojoules per mole. So if we want amount of heat, that would be perhaps in kilojoules, right? We want to get to kilojoules. What do we need in the middle?
Grams.
Well, we have grams on the end. We need moles in the middle. If you're not sure who to put in the middle, try moles. It's often moles. So 15.5 grams of water convert to moles. And then convert to kilojoules. So we got grams down here, so the grams cancel out. Got moles down here, so the moles cancel out. We got the molar mass of water again. 18.016. Yep, 18.016. Use it so often that I just can't even forget it if I try. 6.02 kilojoules per mole. And then it's 15.5 divided by 18.016 times 6.02 equals 3 sig figs are called for. 1792. The unit would be kilojoules. And so we're going to round this up to 5.18 kilojoules. Now, we don't need to have a negative sign on that or a positive sign necessarily because the words are telling us direction. It's the amount of heat absorbed. So this is the amount of heat absorbed when the ice cube melts. Yes? I got the 6.02 from this slide.
And that's constant?
Yeah, that's the heat of fusion for water. It's always the same. Yep.
We need to do heat of fusion
You might need to do the heat of fusion of something else, and then you would be given the resources to find it, find the heat of fusion.
How do you find heat of fusion?
You'd look it up in a table. Yeah. So here's a full heating curve for ice beginning at minus 25 degrees Celsius and ending with steam at 125 degrees Celsius. So starting at negative 25, we're warming up the ice. Once it reaches the melting point, begins to melt, the temperature doesn't change until it's all melted. And then the temperature rises as the liquid water warms up until it gets to the boiling point. Then the temperature stops increasing. The temperature remains constant until all of the water has boiled, turned into the gas state, and then the steam will increase in temperature after that. So correlate sections 1, 2, and 3 with the correct states of water. So what's happening in section 1 there? Right here, what's going on? Ice is melting. And so we've got the solid and the liquid together. How about this line How about this line segment marked 2? That's liquid. How about line segment 3?
You can see the yellow side.
How do you tell? Well, we can tell for water because we know the boiling point and the melting point of water. But also, just from this curve, if you're going from a solid below its melting point to the gas above the boiling point, there's going to be 2 flat places. The lower flat place is melting, and the one at higher temperature is boiling. It's the only time the heating curve flattens out. So this segment here is a solid heating up. Here is a solid melting into a liquid. This is a liquid heating up. And then up here, what do we have? We have a gas and a liquid. So we have the liquid turning into a gas.
Would that be boiling or evaporating?
It would be boiling because we've got this temperature change going on here. Yes?
Just to recap, at the flat points, does the temperature not change because it's not fully vaporized or melted yet?
Yes, because it's in the process of changing state. So the temperature doesn't change. Because we're continually adding heat here. Where's the heat going if the temperature isn't going up? Well, what's happening is all the higher energy particles are leaving. And so the temperature, the average kinetic energy doesn't increase. The high energy particles leave, they go into the gas state, and what's left, we're continually adding heat, but those high ones leave. And so it just stays at the same temperature until everyone has gone into the gas state. And then the temperature increases. It can be a little hard to get your mind around. So there's not a lot of difficult questions in the textbook in terms of using a graph like this, but worksheet 12 is a completely different story. Whenever you have a substance changing state and temperatures changing as well, you need to draw a heating curve so that you can see what's going on. It doesn't have to be to scale, it doesn't need to be pretty, but you need to see what kind of line segments do you have. There's a separate calculation for each line. So the slanted lines where the temperature is increasing, that's where we use Q equals MC delta T. So for this segment, and for this segment down there, and for this guy. That's how you calculate the amount of energy needed. For the flat places, you're going to use the heat of fusion or the heat of vaporization as a conversion factor. So for this one, you're just going to use delta H VAP, heat of vaporization. And for this one, you're going to use the heat of fusion. So what we've done before is we did these segments here where you had something and the temperature was increasing and you had the specific heat capacity and the mass and you figured out how much energy it took. Now we've added this segment where, oh, well, we've got this ice cube melting, how much energy does it take? You use the heat of fusion as a conversion factor. If you want to know, say from this point up to that point, what you do is you do a calculation for each line segment and then you add them together. Are we going to have this on the test? Not one this big, no. Could there be like 2 or 3? That's possible.
Well, how would the questions be asked? I don't get it.
Well, here's an example of how the question would be asked. I'm glad you asked. Calculate the amount of heat in kilojoules needed to convert 1 mole of ice at minus 25 degrees Celsius to water at 37 degrees Celsius. So we need to draw a picture, a heating curve. Yeah, it's tiring. So here's energy being added, and this is temperature. So what temperature is our thing starting at?
Negative 25.
Negative 25. So let's start it right down here, and we're going to call that minus 25. And what's it going to? 37. Okay, this is ice, frozen water. We should know the melting points and boiling points for water. Water melts at 0 degrees Celsius. So what happens is we've got this ice and it's at minus 25. They told us it was ice, but we can also tell that it's ice at minus 25 because it's below zero. So that's going to warm up until it gets to what temperature?
36.
Nope,
0.
0. It's going to warm up until we get to 0, and then the ice is going to melt. As the ice is melting, the temperature doesn't change. Once all the ice melts and we have water and we continue to heat it, the temperature of the water will increase, and it will increase up to the 37 that the problem tells us to stop at.
But how can you make that justification that that's the correct line?
At 0?
No. Like how you went up.
Oh, like the slope or something?
No, the straight line.
Th-
How did
this
you know
one?
that straight line was that? No.
This
The
straight
horizontal
line.
one?
This one?
That's straight, right?
Yeah, it is straight. Yeah.
So how do you know that's the correct side of that line, or does that not?
Oh, the
matter?
size of it doesn't matter.
Okay.
This is just our little sketch so that we can have an idea of what we're doing.
Oh, okay.
Yeah, I'm a visual person, and I need to be able to see this, at least in my mind. So this is what my mind is seeing. Now, this here, this one, this is to scale.
Right.
And so we see that it takes a lot less energy to melt that particular amount of water than it does to boil it. It took a lot more energy, from 15 to about 55 kilojoules. So that was a lot more. But we don't need to be that careful or picky. We can just do quick and dirty, ugly little sketch here. What this does, though, is it tells us I need to do 3 separate calculations.
Oh.
So I'm going to call them A, B, and C. So this is A, and this is B, and C. For each line segment, there's a separate calculation, and then you add them together at the end. So for A, what I've got going on there is I've got solid water being heated. It's going from minus 25 to 0. A temperature change. We're going to use Q equals MC delta T. Q equals MC delta T. Well, what's the mass? They didn't give it to us. It's 1 mole. Bless you.
So it's like
18.01 grams. So you could write that all out if you want to. 1.00 moles times 18.016 grams per mole. And then you look at that and you say, oh, I didn't even need to do that. Oh, well. 18.016 grams. So the mass is 18.016 grams. The specific heat capacity, so they gave us some stuff here because we're going to need it. We want to use the specific heat capacity of ice. So it's 2.09 joules per gram degree Celsius. 2.09 joules per gram degree Celsius.
You want to use the heat capacity of water?
Because water is liquid and ice is solid. And they're not the same. So we're talking in line A, we're talking about ice, so we need to use the value for ice. The temperature change, it's the final minus the initial. The final is 0, the initial is negative 25. 0 minus negative 25 is positive 25. 25 degrees Celsius. Our units cancel out very nicely. And so for segment A, we get 18.016 times 2.09 times 25. 941.336. Sig figs, 25 has 2 sig figs. So we got 2 sig figs there. And the unit is joule. Make sure you write that down. So line segment B. This is the melting of the ice. We warmed it up to the melting point, and now it's going to melt. There's no temperature change here. This is where we use the heat of fusion. So Heat of fusion is 6.02 kilojoules per mole. We need the moles. Oh, they gave us the moles, so that's nice. 1.00 mole times 6.02 kilojoules per mole. So that's going to end up being 6.02 kilojoules. The flat ones are a little easier. And then C, we've got the water warming up from icy cold to body temperature. So from 0 to 37. So temperature changing, again, we're going to use Q equals MC delta T. The mass of the water has not changed. We still have 1 mole. It's 18.016 grams of water. The specific heat capacity, now it's a liquid, so we want to use the specific heat capacity of liquid water, 4.184. 4.184 joules per gram degrees Celsius. And the temperature change, we're going from 0 to 37. Final minus initial. 37 is the final temperature, the initial temperature is 0. So the temperature change is 37 degrees Celsius. We got 18.016 times 4.184 times 37 equals 2789.02 2 sig figs again, joules. They're asking for the amount of heat in kilojoules. I've got 2 of these in joules and 1 in kilojoules. And these numbers are kind of large, and so let's convert these to kilojoules and then add them together. So if I want kilojoules, I'm dividing by joules. Kilo means 10 to the 3, so I'm dividing by 1,000. So this is going to be 0.94. And I'm going to only keep 2 extra digits, get rid of the rest of those, kilojoules. And down here we're doing the same thing, times 1 kilojoule over 1 times 10 to the 3rd joules. And so this is going to be 2.789 kilojoules. I'm going to take this one, and this one, and this one, and add them together.
Mrs. K,
Yes?
can you add the joules together before converting as well?
You could. You could add A and C together and then convert. I don't see any advantage in that. So now we got 0.9413 kilojoules plus 6.02 kilojoules plus 2.789 kilojoules. Calculator says 9.7503. We're adding. So for sig figs, this one has 2 decimal places, 2 decimal places, 1 decimal place. So I should round this to the first decimal place. And we're going to call that 9.6 and, no, 9.8, sorry. 9.8 kilojoules. There's lots of little steps in there. This is something that you really, really need to be able to write down clearly so that you can see it while you're doing the problem, right? This is one that I would if I, was taking a test, I would not just try to do this on my calculator without writing stuff down. I might get it right, but I might not. If I care about the answer, I'm going to write it all out so I can prove to myself that it's okay. Any questions? Yes?
You know what delta,
Mm-hmm.
isn't it the initial minus the final?
No, it's final minus initial.
Final minus initial.
Yep. It's always,
How come you didn't do it for A, B, C?
well,
For A and C?
I did. I just talked about it. I didn't write it out. So for A, delta T is the final minus the initial. So the final temperature is 0. The initial temperature is negative 25. So 0 minus negative 25 equals 0. Yeah. 0 minus negative 25 is 25.
Yeah, I see.
Yes?
So how do we know, what equation to use for what?
That's a good question. How do you know which equation to use? How do you know whether you use delta H for A or Q equals MC delta T?
Because the temperature changed.
Because the temperature changes. You could try using Q equals MC delta T for all of them. But what you're going to find if you try to do it here is that the temperature didn't change, and so you're going to end up with 0, and that can't be right. If the temperature changes, you use this. If it doesn't change, you use delta H.
So for, like, in any problem, if we flip it, then we can just use that ratio, that,
The delta H. Mm-hmm. Mm-hmm.
Always like that for liquid? You would use the moles times the
Well, for anything melting or freezing, it's heat diffusion. Regardless of which direction you're going, it's the same number. And for boiling or condensing, it's a different number, but it's going to be the same for that substance under all circumstances. Any question?
Can't you also use the area under the curve?
You could use the area under the curve, but how are you going to figure out what it is?
Oh, I don't know. Sometimes they give you the picture first. So.
Not going to give you a picture. Actually, what you would do if you were doing it graphically, like with this one, oops, not that one, where'd it go? So if you want to see how much energy it takes to go from here to there, it's actually just this distance. It's not even really an area. So we've talked about transitions between liquid and gas, and between solid and liquid. You can also have a transition between a gas and a solid, or between a solid and a gas. What? That is crazy. It's called sublimation. It's a physical change going directly from the solid to the gas without passing through the liquid, no melting. This happens with dry ice. Do you ever wonder why dry ice is called dry ice? It doesn't melt. It doesn't get wet. It's dry. And it's ice. It's cold. It's solid carbon dioxide. Carbon dioxide does not exist in a liquid state at atmospheric pressure. It sublimes. It goes directly from the solid to the gas state. And this begins to happen as low as minus 78 degrees Celsius.
So dry ice is not water.
Dry ice is not water. It's CO2. So here's a chunk of dry ice. Solid carbon dioxide. Very, very cold. It's not a solid at room temperature. It's a gas at room temperature. So here it is sitting in an iron ring. And we see this like vapor trail down here. And that's not the CO2. What that is the coldness of this cools the air around it. Cold air falls, warm air rises, cold air falls. And so as the air around this gets cold and it falls, when the air is colder, then less water can be present in the gas state and it condenses. And so you're seeing a cloud formed from water condensing out of the air. That's not the CO2. This will just go directly from the solid into the gas state. You have to be careful with with dry ice. I mean, it can be really fun stuff, but it can be dangerous too. I mean, you can get nasty burns, freezer burns. It's really frostbite by freezing your skin. And it also, because it gives off gas, which takes up a lot of space, if it's in a sealed container, it can be pretty dangerous. Yes?
Can you relate that concept to, I don't know, kids or something? Like make an analogy?
An analogy for what?
Or maybe explain, I didn't really get what you just said.
About the little vapor trail?
Yeah.
Well, that was just sort of for general interest. You don't need to understand that. This is a weird phenomenon. There are very few things that do this that we commonly encounter, do this significantly, but dry ice does. Regular ice will also sublime, but it does so much more slowly. And of course, the temperature has to be below 0 degrees Celsius. In cold climates, like I spent much of my life in Minnesota, and in the winter there, it is cold. I mean, people in Central California have no concept what cold is. I mean, negative 40 degrees Fahrenheit, that's not wind chill, that was just the absolute temperature. That's cold. It can go weeks without getting above freezing. So it snows, and the snow just stays there because it's not warm enough to melt. It stays there, but it does gradually disappear. And you're like, how is the snow becoming less? It hasn't been warm enough to melt. This can happen in the freezer too. You're cleaning out the freezer and you find some ice cubes in the trays way in the back, and they're all small and nasty looking. I'm like, how do ice cubes shrink in the freezer? They sublime. The water molecules on the surface of the ice cube have an average kinetic energy, which is very low in the freezer. But some of them are high and some of them are very low. And so if you have one on the surface that has enough energy, it can escape. It goes into the gas state. It's bouncing around inside your freezer. It's going to get cold and condense on something and freeze again. And this is how you get frost building up on the inside of your freezer. It's coming from the other things, from frozen objects. This also happens in frozen foods. Have you ever taken a package of tater tots out of the freezer and you dump them on the pan and you're like, where the heck did all this ice come from in this bag? Who in their right mind would package tater tots with ice crystals, right? That's not on the list. Where did it come from? It came from inside the tater tots. The tater tots had moisture in them, water. The water sublimed out of the tater tots. They didn't melt, but it sublimed out, and it couldn't escape when you opened the freezer door. It was stuck inside the bag. So it forms ice crystals other places. And this is how foods dry out and get freezer burn in the freezer. You can avoid this by packaging them in a way that there's no airspace, by wrapping them tightly in foil and then in plastic wrap, or using one of those vacuum seal bags. Or you can use a colder freezer, a sub-zero freezer, a deep freeze. The colder it is, the less sublimation you have. So there's chemistry saving the food in your freezer. Any questions?